Math 1314, Tyler Junior College, section 4.4, exponential and logarithmic equations. Two more examples of exponential equations. I would be remiss if I didn't warn you that it's not always like you saw in the first two videos. It's not always, oh, the bases match, let's equate the exponents. And it's not always as simple as, hey, let's log both sides and use the power rule. And don't get me wrong, those strategies are the ones that will solve most exponential equations. But sometimes things get a little ugly or unexpected. Let's take the first example. Solve 7 to the x minus 2 power equals 3 to the 5x plus 1 power. You should try to get matching bases, which we won't be able to here. I can't rewrite 7 as a power of 3. I can't rewrite 7 as a power of anything. And before anybody pulls the what about 7 equals 3 to the log base 3 of 7? Okay, technically that would work, but I still wouldn't go there. Not unless you're just trying to be clever or pompous. Let's use our strategy. Our strategy, when we can't get the bases to match, is to isolate the exponential term and then take the log of both sides. But in this one, we have two exponential terms. That's the bad news. The good news is each one is technically isolated. There's nothing outside of the 7 to the x minus 2 power on the left, and there's nothing outside of the 3 to the 5x plus 1 power on the right. So we can go ahead and walk up to this one and take the log of both sides, any base that we want. Let's just use log base 10. Log of 7 to the x minus 2 power equals log of 3 to the 5x plus 1 power. And remember, the purpose of that move was to execute the power rule on the side that has a power. Well, they both have powers, so we use the power rule on both sides. Bring down the x minus 2 on the left. That will be a factor, or a coefficient if you will, of log of 7. And on the right side, same thing, except the power was 5x plus 1. So that's the factor or coefficient in front of log of 3. So why is this any worse than the previous one? Well, we're trying to get x by itself. Okay, except we have two x's, one on the left and one on the right, and they're both buried inside of parentheses, and the thing keeping them in parentheses are logarithms. Now, logs are just numbers. You do the same thing with those that you do with other things. Add, subtract, multiply, divide, distribute. They're just chunky numbers that kind of muck things up. So how are we going to solve this? Well, the first thing we got to do is get rid of the parentheses. That's going to invoke the distributive property. The fact that what we're distributing is a logarithm is almost irrelevant. It just means you have to be careful. For example, if we distribute the log 7 on the left side of the equation, we get x times log 7 minus 2 times log 7. Messy, but correct. And the same thing on the right side. If we distribute the log 3 across the 5x plus 1, we get 5x times log 3. I don't need the dot there. Plus 1 times log 3, but I don't need to write the 1. 1 times anything is itself. Well, that frees up the x's, but we still have x's on both sides. And remember, when you're solving for x, and you've got an x term on both sides, one of them's got to go. But there's another obstacle. Which x do we subtract? Well, what's going to happen as a consequence of it? Well, I don't think it's the best choice here, so we'll just subtract 5x log 3 from both sides. And we have to subtract the entire term. When you're doing an addition or subtraction move, it has to be the entire term. And if you're not sure what I mean by term, in short, a multiplication problem. I can't subtract a piece of this multiplication problem. I have to subtract it as a whole term. And subtract it from the right side, the left side as well. The purpose of that move is easy. Cancel. But what do we get when we combine these? They're like terms in the sense that they both have x's, but they're unlike terms in the sense that their logarithms are different. I can't combine these. If it was just x minus 5x, that's negative 4x. But this has a coefficient, this has a coefficient, and I can't combine those because I don't know what they equal because they're logs that I haven't answered yet. So what do we do with this? The answer is just write it down. X log 7 minus 5x log 3. So basically I just moved the 5x log 3 from the right to the left. Speaking of the left, I still have this minus 2 log 7. I don't want it on that side, and the reason I don't want it on that side is it doesn't have an x. So I'm going to do two moves at once. I'm going to move the x term from the right to the left, and I'm going to move the non-x term, 2 log 7, from the left to the right by adding it on both sides. This is what I call segregating the x terms. Please don't read anything in my use of the word segregate here. It simply means to put one thing over here and another thing over there. I'm not making any allusions to the historical context of the word. By segregating the x terms, that means put all the x terms on one side, put everything else on the other. If we put all the x terms on the left, we get this. If we put the other terms on the right, we get log of 3 plus 2 log of 7. Okay, but that doesn't fix the problem of having two x terms. I still have two x terms over here. They're just on the same side now. Some of the best math students had trouble solving for x here. Full disclosure, when I first ran into a problem like this, I could not figure out how to finish it on my own. As much as I hate to say it, it took a physics major to show me, hey, all you have to do is, and I hit myself for having to have a physics major tell me how to do math. I made sure that never happened again. Nothing against physics majors. That's just the theoretical mathematician in me bubbling to the surface. How do you finish solving this? You get all the x terms on one side so that you can factor out the x. Basically the distributive property backwards. If I factor out the x on the left, I get log of 7 minus 5 log of 3. And nothing's happened on the right. Log of 3 plus 2 log of 7. And it doesn't look any better than it was, but it's leagues better. Because now it has, not only does it have just one x, the only reason this x isn't by itself is because it's multiplied by something. And by now we should all know how to get rid of something that's multiplied, divide. Granted, the thing that's multiplied by it is a big chunky subtraction problem with 2 logs, but it doesn't matter. That's just a number. And if we divide both sides by that number, if we divide both sides by log of 7 minus 5 log of 3, log of 7 minus 5 log of 3, then we can cancel out this huge factor, and now we have x equals log of 3 plus 2 log of 7 on top, all over log of 7 minus 5 log of 3 on the bottom. Mission accomplished. I solved for x. Want an approximate answer? Get out a calculator and see what happens. I owe it to this problem to get its approximate solution. Let's see, you gotta be very careful here because of the fraction. A good rule of thumb for putting big chunky fractions in calculators: throw an extra set of parentheses around chunky numerators and or chunky denominators. Parentheses, log 3, close the logs parentheses, plus 2 log 7. Close the logs parentheses, close the fractions parentheses, divided by open parentheses, log 7, close the logs parentheses, minus 5 log 3, close the logs parentheses, close the denominators parentheses, and I get to 4 decimal places about negative 1.4069. Is that really the solution? Well, substitute it into both sides of this equation and see if you get approximately the same values. Assuming everything went well, and I'm crossing my fingers and hoping it did because I don't want to refilm this video, it's the correct solution. Dare I? How much time have we gone into? I'm afraid it's already too long unless we've got one more example to go through. I'm not going to do it now, but I'm going to do an optional video after this one to show you a really, really unorthodox thing you can do with this answer, but I'll save that for an optional video following this. Let me save that answer though. Log of 3 plus 2 log of 7 over log of 7 minus 5 log of 3. Just to kind of foreshadow what that optional video is going to be, you can actually condense this into 1 log. But I'll save that for the optional video, because in most college algebra classes, that's not even something that's thought of, much less done. But if you've been following this series of videos, you know that I don't approach this like most college algebra classes. Let's solve this other equation. Notice it has 2 exponential terms, e to the 2x and minus 12e to the x. But unlike the previous example that I just erased, there's another term floating around. Why is that a problem? If we're going to solve using logarithms, we're supposed to isolate the exponential terms. If you have 2, one on the left, one on the right, I can't do that here. This 27 has to go on one side, and whichever side it's on, it's going to obstruct the isolating an exponential term. But look a little more closely and start having flashbacks, not back to chapter 3, not back to chapter 2, but all the way back to chapter 1, specifically section 1.6, which was titled Other Types of Equations. In fact, I made an allusion to this about maybe 1 or 2 videos ago. This is a quadratic-like equation. This equation is quadratic in form. And remember what that means. Quadratic in form means you have 2 terms that have the same bases, but one exponent is twice the other. This exponent is twice that. Because this equation is quadratic in form, and for the life of me, I can't remember if I said the phrase quadratic in form or quadratic-like, but regardless, if there are 2 exponential terms, with matching bases, which we have, they're both base e, so if I use logs, guess which one I'm going to use? And one exponent is twice the other. This is exactly the situation that we're in. Then use a substitution. And not only we use a substitution, I can describe exactly what it was. The substitution was to let u be the lesser power, the lesser powered term, and u squared equal the greater powered term. So we're about to make substitution. We're going to let u be the lesser of the 2 exponential powers. That was redundant. Lesser of the lesser powered term, so e to the x. And as a consequence of that, u squared will be the greater powered term, e to the 2x. E to the 2x will get replaced with u squared minus 12. E to the x will get replaced with u plus 27 equals 0. This quadratic in form equation, this quadratic-like equation is now quadratic, thanks to the substitution. And you can solve it using the means of your choice. I'm going to factor, because I built this problem to do that. You could use the quadratic formula. What 2 numbers add to give negative 12, multiply to give positive 27. Negative 9 and negative 3. 0 factor property says set each factor equal to 0. U minus 9 equals 0. U minus 3 is equal to 0. And if we solve both of those, we get u equals 9 and u equals 3. Ooh, I need to become more ambidextrous. I could do this more often. But we're not done, because that substitution was temporary. If you use a substitution in a quadratic-like equation, you unuse it at the end. Thank you, letter U. I appreciate what you did for me. Give me back the e to the x. e to the x equals 9, e to the x equals 3. And remember that a quadratic-like equation concludes by solving the remaining equations. So I still have to solve e to the x equals 9 and e to the x equals 3. But those are both exponential equations. We can take the log of both sides, and because of base e, we're going to use natural log. We take the natural log of both sides. Natural log of e to the x equals natural log of 9. Natural log of e to the x equals natural log of 3. We can finish this real fast. Power rule brings down the x. Natural log of e is 1. X times 1 is x. You could also write x by answering this log's question. What power turns e into e to the x power? X. Over here the same thing, except we get x equals the natural log of 3. And if we want a decimal approximation, these are easy to put in a calculator. They're just baby logs. Let's see, Ellen, turn on calculator. Natural log of 9 is about to 4 decimal places, 2.1973. If we do the natural log of 3, we get 1.0986. It's actually not uncommon to have exponential equations that are quadratic in form. I don't know why, it just seems to be a popular form of equation in upper level math classes. So those are 2 more examples of exponential equations. One last parting thought before I film the optional video on condensing this into a single log. I know it's not obvious, but this second answer is exactly twice the first. In fact, when I calculated this answer, I didn't take the natural log of 3. I took this and cut it in half. Wait, what? Well, go ahead, take natural log of 3. It's going to equal this, I promise you that. But my question is, how can I justify cutting the first answer in half to get the second? I'll give you a hint. 9 is 3 squared. I love my job.